So I'm going to record part of this presentation, not the full thing. So let's look at these examples. Let x1, x2, xn be a sample from the normal distribution with mean mu and variance sigma square. We will assume that the variance sigma square is known. And suppose we want to test the simple alternative, we denote the value under the alternative as mu naught. So maybe mu naught is equal to 5, say. It's some known numerical value. Under the alternative, mu is equal to some value, we denote it by mu1, and we assume that mu1 is greater than mu naught. Now, because the hypothesis concerns the population mean, our statistic will be the sample mean. Now, we also know that the average value of x bar over repeated samples is the population mean. So, if the alternative hypothesis is correct, we would expect that the sample mean is generally large. So, hence we will base our decision on the difference x bar minus mu naught. So note that if the alternative is correct, we expect this distribution x bar minus mu naught to have some large positive value. Now to decide how large must this difference be for us to start rejecting the null? Let me also standardize this difference. I'm going to standardize by the standard error of x bar, which you may recall is sigma over root n. So x bar minus mu naught divided by sigma over root n, which is root n times x bar minus mu naught over sigma. So I am going to now reject h naught if this quantity is greater than some threshold c. How to choose c? C comes from the fact that I need some pre-specified level of significance. So let me assume that this pre-specified level of significance is alpha. If you remember the definition of level of significance, it means that the probability of rejecting h naught, given that the null is true, must be equal to alpha. So alpha is some value like 0.05 or 0.01 or some known value. So in that case, we want the probability of root n x bar minus mu naught over sigma greater than c. Given that the true mean is mu naught, we want this probability to be equal to alpha. But if mu is equal to mu naught, then this quantity, root n x bar minus mu naught over sigma, it follows the standard normal distribution. So go back and look at the notes on sampling distribution to see this. And hence, we can use this we can compare with the cutoffs of the standard normal distribution, and we can use this to solve for C. It turns out that C is equal to this quantity, mu naught plus sigma by root n tau alpha. Tau alpha is some critical value. It's some quantile for the standard normal distribution. So you don't need to go too much into it. Just note that if the level of significance is 5%, then tau alpha is 1.64. If it is 2.5%, it's 1.96. And if it's 1%, it's 2.33. So generally, the smaller the level of significance, the higher the value of tau alpha. So this is how you get tau alpha. These quantities are known for the standard normal distribution, and hence we can use the standard normal distribution to get the cutoffs. Suppose we want to calculate the power of the test. So to calculate the power, we have to assume that the alternative is correct. So if the alternative is correct, then in the previous case, we had root n x bar minus mu naught by sigma follows normal 0, 1. In this case, root n x bar minus mu 1 by sigma will follow normal 0, 1. And again, we can use the equivalence with the standard normal distribution and find what is called the power function. So this power function is the probability of the standard normal being greater than this quantity, root n by sigma mu naught minus mu 1 plus tau alpha, where tau alpha is the appropriate tau for the pre-specified alpha. So this is how you would calculate the power of this test. It can be shown that this test we just spoke of is the NP test for this situation. Now, suppose that we replace the hypothesis by the composite alternative mu greater than mu naught. Then by the same logic, you can show that C still has the same value, which is mu naught plus sigma by root n times tau alpha. And the power, which is not a single value now, it depends on the correct value of mu, is now replaced by what we call the power function. So we also typically plot the power function as a function of mu, and the curve we get is called the power curve. So here is an example. Suppose that sigma square is equal to 256 and we want to test H naught mu equal to 200 against the alternative of mu greater than 200, and we want to do this based on a sample of size n equal to 100. So if you look at the previous few slides, my critical region will be that we reject H naught if x bar is greater than 200 plus sigma, which is 16, by root n, which is 10, times 1.64, assuming that we want a 5% level of significance. So this value turns out to be 202.624. So the decision rule is that we reject H naught if x bar is greater than 202.624. The power, similarly, we can calculate as the probability that the standard normal distribution is greater than n by root sigma times mu naught minus mu 1 plus tau alpha. So it's possible to calculate these probabilities either from software or from what we call the biometrica tables. And you have to plug in the particular value of mu because the alternative hypothesis is composite. So we have a power curve. If, for example, your alternative value is 204, you can plug in 204 for mu, do the calculation, and it turns out that you have 80% power. So you have an 80% power, 80% chance of rejecting the null hypothesis if the true alternative mean of the population is 204.
Ma'am, could you explain once more why do we fix type 1 error only and minimize type 2 error?
In general?
Yes,
So
ma'am.
in general, there's no rule as to which you would choose for the null and which you would choose for the alternative. So if you consider the example of a drug, for example, you are testing whether a new drug is more effective than the standard drug. So the two types of error which might occur is you say that the new drug is more effective when it isn't, or you say that the standard drug is more effective when it isn't. So to decide on which you use as the null and which you use as the alternative, you have to decide which is the more serious error. So is it a more serious error to continue giving the standard drug when it is ineffective, or is it a more serious error to start giving a new drug when it might be ineffective? So
Okay.
whichever is the more serious error, we try and fix that probability at some very small level. So we ensure that that probability is no more than, say, 5%, or if I want tighter control, no more than 1%. And then we minimize the type 2 error. So we don't really know how much we will be able to minimize the type 2 error. But we make sure that the type 1 error is as small as we want. So basically, you look at the more serious of the two errors which you can commit, and you control that kind of error.
Oh, okay. Thank you.
Okay, so I'm going to move on to the next set of notes. So this is just recap from what I just said. This is the same example. So in fact, the test which we constructed for the composite alternative for the normal distribution is the UMP test. So we didn't use the Neyman Pearson lemma, but it's possible to show that it's the UMP test. This is just a repetition of the previous slide. Okay, so let's move on to example 1b, where we now want to test mu equal to mu naught against another composite alternative. But this time, under the alternative, we assume that mu will be less than mu naught. So again, we use x bar and the difference, x bar minus mu naught. But in this case, if the alternative is correct, we will expect that x bar on average will be smaller than mu naught. So x bar minus mu naught, we expect will have a large negative value. So as before, we standardize, and this time we reject the null if this quantity is less than some quantity C. In the previous case, we were rejecting if this was greater than the quantity C, because we expected it to be greater under the alternative. In this case, under the alternative, we expect the difference to be very small, in the sense that we expect it to be negative and a large negative value. So we reject if this is less than some C. The previous test was called a right tail test. This is called a left tail test. So using similar kind of calculations, so this is the left tail for the standard normal distribution. By the symmetry of the standard normal distribution, if for the right tail a value of 0.05 corresponded to 1.64, then for the left tail, the value must correspond to minus 1.64. This is because for the standard normal distribution, the distribution is symmetric about 0. So that's basically what this says. And it turns out that after some simplification, the critical region which you get is x bar less than mu naught minus sigma by root n tau alpha. So previously for the right tail test, it was mu naught plus sigma by root n tau alpha, and we reject if x bar was greater than this. If the alternative is of the less than kind, then we reject the null if x bar is less than this threshold. As before, we can calculate the expression for the power or the power function. Now, suppose again that sigma square is 256. We want to test h naught mu equal to 200. This time, my alternative is mu less than 200. As before, I have a sample size of 100. The critical region, based on the previous slide, will now be reject h naught if x bar is less than mu naught, which is 200, minus sigma, which is 16, by root n, which is 10, times tau alpha, which is 1.65. I'm assuming alpha is 5%. Or x bar is less than 197.376. So if the rule is that if I get a sample for which the sample mean is less than 197.3.76, I will reject the hypothesis that the population mean is 200. And this is the expression for the power function. I have to substitute the correct value of mu to get an expression for the power, and I can also plot the power curve. So now suppose we want to test the null hypothesis, mu equal to mu naught, against an alternative which just says that mu is not equal to mu naught. So say we are looking at the average height of Indians and the average height of, say, Pakistanis. The null says that the average height of Indians and Pakistanis is the same. But we don't really know if the alternative is that the height of Pakistanis is greater on average than Indians, or the height of Indians is greater on average than Pakistanis. So we just leave it as a two-sided alternative, which says that they're simply different. They don't have the same mean. For this two-sided alternative, again, we look at the difference, x bar minus mu naught, which is the value under the null. Now, if the alternative is correct, we can either get this value to have a very large positive value or to be a very small negative value. So it can be large in either direction. The more you go away from mu naught, the more likely this kind of a value is under the alternative. So in this case, we will use a two-sided test. We will need two constants, C1 and C2, and we will reject for two situations. Either root n x bar minus mu naught by sigma is less than C1, so this is the left tail, or root n x bar minus mu naught by sigma is greater than C2, which is the right tail. The type 1 error is now the sum of both these two probabilities. The sum of both these two probabilities, assuming that the correct value of mu is mu naught, and we want the sum of these two probabilities now to be equal to alpha. So because of the symmetry of the distribution, it turns out that we should use a probability of alpha by 2 on either tail. So if we want an overall level of significance of 5%, we should use a 2.5% probability in either tail. So by symmetry, my C1 is equal to minus C2, and the tau alpha in the previous examples will now be replaced by tau of alpha by 2. So for the two-sided alternative, the critical region turns out to be reject H naught either if x bar is less than mu naught minus sigma by root n tau alpha by 2, or x bar is greater than mu naught plus sigma by root n tau alpha by 2. So the form is very similar to the right-tailed or the left-tailed test. The only difference is that alpha is now replaced by alpha over 2. And similarly, we can write down the expression for the power function of the test. It will be the sum of two quantities. So again, consider this same example where sigma square is 256. We are testing H naught, mu equal to 200. This time, my alternative is mu is not equal to 200. I have, as before, a sample size of 100. So if I substitute the previous values, it turns out that I will reject H naught if either x bar is less than 200 minus 16 by 10. So note that my previous multiplier of 1.64 is now replaced by the multiplier of 1.96 because my tau alpha is now replaced by tau alpha by 2. So if I assume that I want an overall level of significance of 5%, I have to now use the tau corresponding not to 5%, but corresponding to half of 5%, which is 2.5%. So that value is 1.96. So this is the left tail of the test, and the right tail of the test says we will also reject if x bar is greater than 200 plus 16 by 10 into 1.96. So we reject if x bar is very far out from 200, but it might lie in either tail. So either it's less than 1.96, 0.864, or it is greater than 203.136. So note that these two values are symmetric about the value under the null hypothesis, which is 200. Now, we assume that sigma square was known. It's quite rare that sigma square is known. It might happen in certain lab experiments where we have control over how much variability there is in the observations, or we have some prior idea of the variability of the test procedure which we are using. By test, I mean the lab test. But in general, for say a field survey, an observational survey, we don't really know the value of sigma square. So if I ask you what is the average variability in height of an adult Indian, we don't really have any definite guide on that. So we need to generalize the test from the case where we have an underlying normal distribution. We still have the underlying normal distribution, but in this case, sigma square is unknown. So let me suppose that I want to test H naught, mu equal to mu naught against mu greater than mu naught. So just as before, we can argue that the reasonable test is to look at root n x bar minus mu naught over sigma and argue that if the alternative is correct, then we will expect this to be large. So we will reject the null if this is greater than some quantity c, where c is calculated based on considerations of the level of significance. The only problem with this is that I can't really calculate this quantity because I don't know the value of sigma. So since I don't know the value of sigma, the logical thing to do is to replace it by its sample counterpart. So the sample counterpart is the sample variance, and I will use a divisor for the variance, which is n minus 1. So we can define the sample variance both with a divisor of n minus 1 as well as with a divisor of n. In this case, I'm going to use this divisor of n minus 1. The reason I use this divisor of n minus 1 is if I do, then the sampling distribution of this quantity, root n x bar minus mu naught by s, is known. So if the null is correct, it's possible to show that this is of the form of a standard normal in the numerator and root over a chi-square variable divided by its degrees of freedom in the denominator. So go back and look at the slides on sampling distribution to see this. And it follows that if the null is true, this follows a t distribution with n minus 1 degrees of freedom. So we can use the tables of the t distribution to find the cutoff. We want that the probability of rejection under the null hypothesis to be equal to some pre-specified alpha, which again suppose is 5%. So we want the probability that root n x bar minus mu naught over s greater than c, given that mu equal to mu naught is equal to alpha. But we just saw that this quantity, if mu is equal to mu naught, will follow a t distribution with n minus 1 degrees of freedom. So we need to use the condition that probability of t with n minus 1 degrees of freedom greater than c is equal to alpha and solve for c based on this requirement. So we use the notation C is equal to T subscript n minus 1 alpha. So what that means is, if I plot the probability distribution function of the T distribution, then this quantity T n minus 1 alpha is the point which corresponds to a probability of alpha in the right tail. So it's possible to get this again both from tables as well as from software. And plugging in this value of C, my critical region is that I will reject H naught if X bar is greater than mu naught plus S over root n T n minus 1 alpha. So two things change from the normal situation. My sigma is now replaced by S, and my tau is now replaced by the corresponding cutoff from the T distribution with n minus 1 degrees of freedom. So as before, we can also write down the expression for the power and calculate it and plot the power curve. So note that the cutoff, I told you some of the cutoffs for the standard normal. I can't really do that for the T distribution because the cutoff will depend on the degrees of freedom. The degrees of freedom is n minus 1, and n will depend upon your sample size. So you either have to look up the T table for your choice of sample size, or you have to use some software to get the appropriate cutoff for the T distribution. So generally, we will expect them to be in the region of 2. By the same logic, if we want to test H naught mu equal to mu naught against mu less than mu naught, we will get the left tail test. So, or we can also test for a two-sided alternative and get the critical region for the two-sided test. So note that in all cases, it appears to look like the normal test, except that my sigma is now replaced by S and the tau is replaced by the corresponding critical value from the T distribution, the correct T distribution, which is the T distribution with n minus 1 degrees of freedom. Now, these were tests for the normal mean. We might also want to test for the normal variance. So variance, for example, relates to the variability of measurements. You can think that maybe you have a test procedure, you have a new test procedure, and you want to test if the variability of the new test procedure is the same as the variability of the standard test procedure. So if it is greater, you might not want to change to the new test. If you don't have enough evidence to conclude that it is greater, you might want to switch to the new test if it is perhaps a cheaper test. So this is an example of a situation where you might be interested to test a hypothesis about a population variance rather than a population mean. So as before, we have a sample from a normal distribution. We want to test sigma square equal to sigma naught square. Let's suppose that the alternative is of the form sigma square is greater than sigma naught square. So sigma naught square is some known value. So maybe sigma naught square is 100. We want to test if the correct variance is 100 or it is greater than 100. So let's suppose mu is unknown. When we were testing hypothesis about the population mean, we use the sample mean. So by the same logic, since the hypothesis concerns the population variance, we are going to use the sample variance. And because I know the distribution of the sampling variance when I have a divisor of n minus 1, I'm going to use this definition of the sample variance, which is the variance but with the divisor of n minus 1 rather than n. Now, if the alternative is correct, we will expect this ratio S square by sigma naught square to be large. Under the alternative, sigma square is greater than sigma naught square. So since S square is an estimator of the correct population variance, if the correct population variance is a lot larger than sigma naught square, we will expect the quantity S squared by sigma naught squared to be large. So how large? So we can multiply by n minus 1. It doesn't really matter. Let's say that we will reject if n minus 1 S squared by sigma naught square is greater than C. So C is the cutoff for the right tail test. And using the fact that under the null hypothesis, this quantity n minus 1 S squared by sigma naught square, it follows what is called a chi-square distribution with n minus 1 degrees of freedom. Again, do a recap of the notes on sampling distributions to refresh your mind about this. So the chi-square distribution is another sampling distribution, and we can look up the either tables or software or make a plot like this for the appropriate chi-square distribution to find the cutoff value. So note again that I'm not really able to give you some cutoff values because the cutoff will depend on the degrees of freedom, which in turn will depend upon your sample size. So we use similar kind of notation, C equal to chi-square n minus 1 alpha, which means that C is the cutoff for the chi-square distribution with n minus 1 degrees of freedom. It is that point such that the probability or the area to the right is some pre-specified alpha. So we can obtain these from what we call chi-square tables. We can also obtain these from any standard software. So my critical region turns out to look like this. We reject H naught if S squared, which is the sample variance with divisor n minus 1, is greater than this quantity. Sigma naught square, the value under the null, divided by n minus 1 times chi-square n minus 1 alpha. So just like for the normal distribution, we can write down the expression for the power function. If we want to do a left tail test, so this would say that the variability is some pre-specified sigma naught square against the alternative that it is less than sigma naught square. So we can proceed similarly, and we can see that the critical region will turn out to be very similar, except that my chi-square n minus 1 alpha is now substituted by chi-square n minus 1 and 1 minus alpha. So this means it is that point such that the area to the right is 1 minus alpha, or equivalently, the area to the left is alpha. So this is my left tail test if I have an alternative of the form sigma squared less than sigma naught squared. So this is the point. If my alpha is 0.05, then I have to look up the correct chi-square distribution for my sample size, and I can calculate this value. So here is an example where we are sampling from normal mu sigma square. Mu is unknown, but my hypothesis doesn't concern mu, it concerns sigma square. I want to test whether sigma square is 20 against the alternative that it is, say, greater than 20. So say we have a sample of size 25, and based on my sample, it turns out that my x bar is 400 and my S square, which is the sample variance with divisor n minus 1, which means 24, is 25. So I have to look up, I will have a right tail test, and the degrees of freedom for the chi-square is n minus 1, which is 24. So I have to look up the critical value corresponding to 24 and the probability being 0.05, assuming that I want to test a level of significance 5%. It turns out that this value is 36.42. So my n minus 1 S square by sigma naught square, it turns out to be equal to 30. And since it is less than the cutoff value, which is 36.42, my decision is that I do not reject H naught. So I don't have enough evidence to conclude that sigma square is greater than 20. Now, if mu was known, then I would use a different definition for the variance. So typically when we calculate the variance, we assume that this is the sum of square deviations from the sample mean. If mu is known, then we would plug in the population mean instead, and we would use a divisor of n. So this again is obtained from the fact that we know the sampling distribution of this quantity. So again, you can refer to the notes on sampling distributions to see that in this case, this quantity n s square by sigma square, it follows a chi-square distribution, this time with n degrees of freedom. And by the same logic, we can see that the critical region will be of the form n s square, where square is now this quantity, by sigma naught square greater than chi-square n and alpha. So that value of chi-square with n degrees of freedom, which has a probability alpha to the right. Now, all of these were one sample problems. Suppose we have two populations. So I gave you the example of two drugs, a standard drug and a new drug. So maybe we have some patient data. So perhaps a drug for reducing blood pressure, and we have the blood pressure of two sets of patients, one given the standard and one given the new drug. So let me assume that I have two samples. More generally, let me assume that I have two samples. The first one is of size n1, and it's from a population which is normally distributed with mean mu1 and variance sigma 1 square. And I have another sample from a different population. Let me assume that this sample is of size n2. It's not necessary that the two samples will have the same size. And this is a sample from another normal distribution with mean mu2 and variance sigma 2 square. Now we are interested in the difference between the two means. So we might want to test, for example, if the mean height of men and of women differs by 4 inches. So in this case, we want to test, if we assume mu1 corresponds to men and mu2 to women, we want to test mu1 minus mu2 is equal to 4. Now, if we might also want to test that the mean height is the same. So in that case, my mu1 minus mu2 is equal to 0. So theta is equal to 0. So this is the most common of the two sample tests, where we want to test that two distributions have the same mean. Now, how we test it will depend on what we know about the sigma square and what we are able to assume about them. For the simple case, assume that sigma 1 and sigma 2 are somehow both known. So in that case, my test statistic will be this standard quantity. I will look at the difference of the corresponding sample means, x bar minus y bar. From this, I will subtract theta. So what is theta? Under the null hypothesis, I am saying that the difference between mu1 minus mu2 is equal to theta. Theta is some known quantity, like it was 4 for the difference in heights, or it could be 0 if you're saying that the two mu's are the same. Under the alternative, let me suppose that I have a one-sided alternative which says that mu1 minus mu2 is greater than 0, greater than theta. So if the alternative is correct, I would expect x bar minus y bar to be greater than theta, or I would expect the numerator of this test statistic to be large. I standardize by the variance. So note that you should be able to do this calculation. Variance of the quantity x bar minus y bar is sigma 1 square by n1 plus sigma 2 square by n2. This is because I'm assuming that the two samples are independent. So if I use the fact that the sampling distribution of this quantity is normal 0, 1 under H naught, I will reject H naught at some level alpha if this is greater than tau alpha. So I can simplify this to get my cutoff value for the difference x bar minus y bar. So just like I have mu1 minus mu2 greater than theta, I can also think of this mu1 minus mu2 less than theta, or mu1 minus mu2 not equal to theta. However, sigma 1 and sigma 2 are rarely unknown. We're going to look at Fisher's t-test, which is one of the most well-known tests. But to use Fisher's t-test, I have to make an assumption. This assumption is that sigma 1 is equal to sigma 2 is equal to some common value. So I have to assume that the two populations whose means I'm comparing have the same population variance. So if I do that, then it turns out that this quantity on the last line, x bar minus y bar minus theta divided by, now I would like to have sigma here, and then root over 1 over n1 plus 1 over n2. That would follow a normal distribution. Now, because I don't know this common value sigma, I'm going to replace it by its best estimator. So it turns out that the best estimator is what we call the pooled variance. So basically, you have to look at the first sample, find the sum of squared deviations from its mean. Similarly, for the second sample, the means are different. In this case, you use the mean of the second sample. You add them, and then you have to divide by this quantity, n1 plus n2 minus 2. So if you do that, we have this what we call the t statistic. And it turns out that if the null hypothesis is correct, this will follow a t distribution, and the degrees of freedom will be n1 plus n2 minus 2. So we reject h naught at level alpha if this is greater than the corresponding alphath percentile of the distribution, where you have to look up the alphath percentile from the tables or software. When I say alphath percentile, I mean that value for the t distribution with n1 plus n2 minus 2 degrees of freedom, which has an area of alpha to its right. So just like that, and because the t distribution is symmetric like the normal distribution, we can also derive the left tail test for the case when sigma square is unknown and we want to compare two means, or we can derive the two sample test. So I'm going to stop here for today. Do you have any questions? Okay, in that case,